Okay, let's talk about some bivariate inferential statistical tests. So by bivariate, I mean, let's break this word down. Variate, the root there is variables. Bi means two, right? Like in bicycle. So bivariate tests are statistical tests that include two variables. In more advanced statistical classes, you'll learn that there are multivariate tests where you can put lots of variables into the statistical test you're going to run. But in this course, where it's a basics class, we're sticking to bivariate. And there's four key tests I want you to know. There are definitely more than these four, but these are some of the most common ones. And if you know these four, you can basically test the relationship between any two variables, quantitative variables, of course, in a data set that you have. So here are the names of the four tests. There's t-tests, there's the ANOVA, there's the Pearson's R, and there's a chi-square test. And they each have a symbol representing the test. So a t-test, just use a lowercase t. The ANOVA, all caps, by the way, ANOVA, all caps, it stands for analysis of variance. The symbol it uses is a capital F. The Pearson's R uses a lowercase r, and the chi-square test uses the Greek chi symbol squared, so a superscript 2 next to it. So how do you decide what test to use based on the two variables you have? It depends on if your variables are categorical or continuous. Categorical are things that are distinct categories, right? Like race, or which branch of the armed services are you in? Or maybe you ask people what their major is, and you have a handful of majors that they're selecting between, as opposed to continuous numbers that are in a sequence that move along, right? Like age in years, or dollars, or temperature, or GPA. So things that are on a scale, continuous data versus categories. So a couple of these tests are what we call comparisons of means. So you know what a mean average is. A t-test and an ANOVA are both comparisons of means. For the t-test, you need, so let's think of this visually. If you want to compare the means of groups, how might you make a graph for that? You'd probably make a bar chart. So say you're comparing the satisfaction score about engagement or workplace satisfaction. So we're an employer, and we're surveying people about their workplace satisfaction, and we want to know if the men or women are more satisfied in working at this company. So they fill out a bunch of questions. It adds up into a scale. That's our continuous variable. And then gender, two groups, male and female in this case, are the categorical variable. You would use a t-test. T-tests are for when one variable is categorical, the other variable is continuous, and your categorical variable only has two groups. That's why I said male or female in this case. Now, as soon as you have a third group or a fourth group in your categorical variable, you move to the ANOVA. The formula, the algorithm, if you will, behind that test is designed for more than two groups, but it's still just a comparison of means. So maybe in this case, we're still at that same company, we still have that same workplace satisfaction score as our continuous variable, but instead of comparing gender, now maybe we're comparing like functional area of the roles. So we have the marketing department versus the sales versus the IT versus HR or something, and we're seeing if different work groups have different levels of satisfaction. The ANOVA can test for statistical significance when there's more than two groups in your categorical variable. Okay, so thus far I've talked about two of these four tests as comparison of means when one variable is continuous and the other variable is categorical with either two groups, the t-test, or three or more groups, the ANOVA. So what happens if both of your variables are continuous? Well, let's visualize this real quick. So first, this is the Pearson's R. It's a test of correlation. You want to see if there's a relationship between the variables in terms of a correlation. So maybe it's workplace satisfaction. Let's stick with our example. But now we have another continuous variable rather than a categorical one on the x-axis. So in this case, maybe it's years of work with the company. How long have they been with the company? We'll say in months. So some people have been there for a few months and some people have been there a long time. And we want to see if there's a relationship. If the longer you work here, does that make you more satisfied with the company or not? And so you can picture a kind of, there's going to be a scatter plot, right? So you've got each person has been there a certain amount of time and has a certain satisfaction score. And so there's all these dots representing different people. And then the Pearson's R is basically figuring out a line of best fit. Is there a positive line? Is there a line that correlates where the longer you're there, the more satisfied you are? Or it could be a negative correlation where the longer you're there, the less satisfied you are. Or there could be like no correlation at all, where some people are satisfied and have been there, not very long and a long time, and some people are dissatisfied and have been there not very long or a long time. But that is what the Pearson's R is doing. It's testing for correlation. And lastly, the logical final test that you would have, if one variable is categorical and one variable is continuous, you do your means test, the t-test or the ANOVA. If both variables are continuous, you do the Pearson's R. So the only logically remaining test would be one where both variables are categorical. Okay, so let's say in this case, we want to know, all right, we'll stick with the same example. So we've got the different work groups as categories, HR and accounting and IT and marketing. I suppose we'll also go with gender, or we could go with race. Maybe there's a few categories, Black, white, Hispanic, Asian, etc. And so what would kind of data visualization would you imagine for this? If neither of them are continuous, then you're going to have something that looks like a crosstabs, basically like a little table where you have your different categories on one side, and your other categories of the second variable on the other, and then you're going to see how many people fall in each cell. So do you have, whether it was gender or race, do you have a sort of evenly distributed number across these different work departments, or are some departments clustering more than others with particular gender or race, say? So those are two different examples, but that's what the chi-square would test for, is the distribution across these cells statistically significant or not? So all of these four tests, these four bivariate tests, which allow you to compare two variables, are basically testing to give you a test statistic. The test statistic would either be, it would say like T equals, or capital F equals, or lowercase r equals, or the chi-squared equals, and it would give you a number. And then that number goes into a formula to give you a p-value. And then that p-value allows you to determine if the distribution or the relationship or the comparison of means is statistically significant or not. So you already learned about the p-values, but now you need an inferential statistical test to give you that test statistic to figure out what your p-value is. And then you determine if you accept or reject the null hypothesis.